In the previous video, we looked at the materials, the energy band diagrams of the materials before they were put into contact by themselves. So now let's make a junction. Let's put the metal against the N-type material. And now what's going to happen is that the Fermi levels in the two materials are going to align. So we're going to have the Fermi level at the same energy throughout the metal semiconductor junction. But how does this happen? Because if you remember, if we look at, let's go back to the previous slide, the Fermi level in the semiconductor is a little bit higher than the Fermi level in the metal. And so we want these Fermi levels to now align when we put them into contact. So that means I'm going to have some electrons going from the semiconductor side into the metal side to try to even out those Fermi levels. Okay, so that's shown in this band diagram. Okay, so the Fermi level is now constant throughout the metal semiconductor junction. But in order for that to happen, I had electrons that had to flow from the semiconductor into the metal. Okay, and those electrons, when they left the semiconductor, they left behind positive charges. And so that resulted in a creation of a depletion region, just as in the case of a p-n junction. Except now the depletion region is only on the semiconductor side of the junction. Since we have all these positive charges now in the semiconductor, that's going to cause the bands to bend upward because it looks a little bit more p-type in this depletion region. So that's why these bands are bending upward. You can also get some negative charges attracted to the interface from the metal side to try to balance out those positive charges. And as a result, we will get an electric field in the depletion region, just as how we had in a p-n junction. Okay, so what are the important things in this structure? If we set x equals 0 to be the metallurgical junction, then the depletion region would be a width w, and it would go out to this point in the semiconductor, x equals x sub n. We have a barrier for electron diffusion from the metal into the semiconductor. That's defined by this phi sub b naught. So this represents a barrier to electron diffusion from the metal to the semiconductor. And this phi sub b naught is going to be equal to the work function of the metal minus the electron affinity. We have another barrier that would prevent electrons in the semiconductor from moving to the metal side. So that's this barrier here, this built-in potential barrier, just as in a p-n junction, but now that built-in potential barrier will have a different equation to figure out what that is. That's phi sub b naught. Oops, minus phi sub n. Let me erase that. That's phi sub n. Okay, so that's this variable here. And phi sub n, this is an earlier definition that we had, so that's just the difference between the conduction band energy and the Fermi energy in the semiconductor.